Today we're going to talk about strong acids and bases, what those are, and simple pH calculations. To start off with, not all acids and bases are equal in strength. There are strong acids and weak acids, there are strong bases and weak bases. But that doesn't necessarily mean how dangerous something is. You can have a very concentrated weak acid be just as deadly as a moderately concentrated strong acid, and the same thing is true with bases. So, what's the difference between strong and weak in these terms? For us, strong and weak refers to the ability to dissociate in water, to come apart in water. It has to do with how well the particular acid or base dissociates. Acidic or basic species that dissociate completely, which means 100% in water, are considered strong. So again, that does not mean that it's deadly, it just means that it comes apart completely 100% when you put it into water. And any acidic or basic species that dissociates less than 100% is considered weak. So that's what those terms actually mean, strong acids and strong bases versus weak acids and weak bases. It's not about the dangerousness of it, but about how easily it comes apart in water to form ions. So for example, HCl, hydrochloric acid, is a strong acid. In water, it comes apart completely according to this equation. So hydrochloric acid starts actually as HCl gas, hydrogen chloride gas. If you bubble that through water, it turns into hydrogen ions, aqueous hydrogen ions, and aqueous chloride ions. And this happens 100%. All of this, 100% of this dissociates. 100% of the HCl dissociates into these two ions. Okay, so we get the hydrogen ions, right, which are also hydronium ions, that H3O+, okay, in case you've forgotten, okay, and chloride ions. Now, what would a weak acid do in comparison? Well, this one right here is hypochlorous acid, okay, it's just got that single oxygen on it, HClO. This is a weak acid, so in water it comes apart less than 100%, meaning that not all of it forms the products on the right. Only some of it forms the products on the right. It comes apart less than 100% and can easily reform the initial acid. So some of it will form the hydrogen ions and the chloride ions, okay? But some of it will also, the hydrogen ions and chloride, this is a hypochlorite ion, excuse me, okay? Some of these will also turn back into the original HClO, whereas up here, once this comes apart, these are the only two things that exist. This doesn't exist anymore. Okay, here, when this comes apart, it can also go back and form the original HClO. And for that reason, you'll see a double arrow here, okay, meaning that this can go in the forward direction or the reverse direction. Okay, so as I was just saying a moment ago, the reaction can go both ways, reforming the initial HClO easily. And weak acids and bases tend to dissociate less than 10%. So up here, 100% of it, okay, turns into the products. Here, only about 10% of this comes apart. So that means that something less than 10%, kind of 10% is the maximum. That means that 90% of it stays as the original weak acid formula, okay? But this side over here is what actually makes it acidic because it's increasing the hydrogen ion concentration. All right, up here, all of it, all 100% of it came apart into hydrogen ions. That's the difference, okay? Now, if you have equal concentrations of both of these things, this first one is more dangerous. But the second one, if this is way more concentrated than the first one, well, then this one is more dangerous. So don't think that just because something is a weak acid means that it's completely safe. If it's very concentrated weak acid, it can be just as bad for you as some dilute strong acid. So you do have to be careful with that. Okay, and I don't remember if this is exactly 90-10 for this particular acid, but 10% is kind of the maximum for any weak acid. Okay, and the same situation is true for strong and weak bases. Anything that is a strong base, 100% of it comes apart in water. And if it's a weak base, something like only 10% of it comes apart in water. So here we have a list of strong acids and strong bases. Telling you right up front, memorize this list. It's not that long, okay? You need to know this list. And the reason why is if you know what's on the list of strong acids and strong bases, then everything else is weak. Okay, this is a much shorter list than the weak acids and weak bases. So if you can remember these, okay, then you can figure out all of the weak substances. Some helpful hints here for strong acids. Notice We've got some binary acids, hydrochloric, hydrobromic, hydroiodic. Note that HF is not on this list. Okay, it is a weak acid. And then the other ones are nitric acid, HNO3, perchloric acid, HClO4, and then sulfuric acid, H2SO4. Now, there are more than the list that's on here. Okay, there exist more strong acids than simply these. But those are the ones that we are going to ask you to know. Okay, and then strong bases: lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide, calcium hydroxide, strontium hydroxide, and barium hydroxide. You'll note for this particular one, okay, how can we remember this, right? So here's the periodic table. Okay, kind of looks like this. All right. If you note here, okay, we're talking about, if we look carefully, things that are in the family 1A: lithium, sodium, potassium, rubidium, cesium, right? Lithium, sodium, potassium, rubidium, and cesium. I guess I can draw one more line in here, and there's technically another one, but that's okay. Okay, francium hardly exists at all in nature, so we don't really include that on this list. But all the ones that are 1A metals locked up with a hydroxide are going to be strong bases, and, okay, ignoring beryllium and magnesium here, but calcium, strontium, and barium. Okay, so if I mark these boxes here, so we got this one, this one, this one, this one, and this one, and then those three right there. Okay, combined with hydroxide, okay, will be the list of strong bases. Okay, so that's the way to remember it. Right up here for strong acids, you've got members of the halogen family plus nitric, perchloric, and sulfuric acids. Down here for strong bases, 1A metals with a hydroxide, and some of the 2A metals, calcium, strontium, and barium, mixed in with hydroxides as well. Remember this list. You need to know this list to identify what is strong. Okay, if you know the strong acids and strong bases, then if it's not on that list, it must be weak. So why was the list on the previous page important? Well, that's because it tells us which acids and bases dissociate completely, dissociate 100%. It also allows us to determine the relative strength of strong acids and strong bases easily using something called the pH scale or the pOH scale, okay, if it's a base. So what's the pH scale and the pOH scale? Really what this means is the power of hydrogen if it's an acid, or the power of hydroxide if it's a base. That's really what that means: power of hydrogen, power of hydroxide. So this is a scale that easily indicates the levels of hydronium or hydroxide present in a solution. So being able to calculate and understand pH is necessary for many industrial processes and important things. A lot of food and soap production requires specific pH. Many products are labeled pH balanced, meaning they are within an acceptable usage range. Things such as public pools must maintain pH levels to keep the pool from growing bacteria or carrying other diseases. So it's a scale that indicates how much hydronium or hydroxide is in your solution. That's what this is. So how is it calculated? pH, okay, here are the important equations for the day, right? These two right here, okay? It's calculated by the following. pH is equal to the negative log of the hydronium ion concentration, okay? So you can also see that as negative log of the hydrogen ion concentration, because you should remember, we've said this now several times, the hydrogen ion concentration for our purposes is the same thing as the hydronium ion concentration, because if you put H plus in water, it is going to turn into H3O plus. It's going to react with water to form hydronium. That would calculate pH for you, negative log of the hydrogen ion concentration or hydronium concentration, however you want to think of it. pOH, the power of hydroxide, is equal to the negative log of the hydroxide ion concentration. Okay, so we're talking about concentrations. That's why we spent that time talking about how to calculate molarities. Hopefully you have not forgotten how to do that. Both of these equations should give you a value between 0 and 14 based on the numbers of how acids and bases work. If the pH is close to 0, the solution is very acidic. If the pOH is close to 0, the solution is very basic. Okay, and then kind of oppositely, if the pH is close to 14, the solution is basic. If the pOH is close to 14, this should say 14, the solution is very acidic. Okay, so they're kind of inverses of each other. All right. So together, these numbers then act as complementary according to the following equation. Okay, so if you calculate pH and pOH of a solution and you add them together, it will equal 14. And that's a property. This equation down here, while we're not going to use it really today, is going to be one that we are going to use in the future. The one that we can manipulate and take advantage of to solve for some of these other variables back here. But right now, today, we're just focusing on really these two equations first. All right, how to calculate pH, how to calculate pOH. Okay.
So Mr. Nedick here for a second. And I guess it's probably smart to talk about what a log is for just a moment. Okay, yes, these are both logs, but that's not what we're talking about. We're talking about the mathematical logarithm. It's a function, and logarithms are kind of interesting things. You can see the graphs don't make straight lines. They make very curvy lines. And there are different kinds of logarithms, and maybe you've talked about this in math, and maybe you haven't. This is maybe the most common logarithm to day-to-day life, which is log base 10. That's what we'll be using here in chemistry. And you might notice that to go from 1 to 2 on this graph, we have to go from 10 to 100. And yeah, there are other kinds of logarithms. Maybe you talked about the natural log, which is probably the more useful to a math class or whatever. But in this class, we're going to use log base 10. And really, all a logarithm does is it undoes exponentiation, right? It undoes exponents. So if you're going to do this, it's really just a function on a calculator. You could calculate a logarithm by hand, I suppose, although it's kind of painful to do. It's going to be a lot easier to use a calculator. Now, your calculator has different functions for logarithms, and we're after the base 10 log, so the button that's labeled log. And so we're going to be using this log button quite a bit in this class. So I want to make sure we know what we're doing before we go forward. So really quickly, let's take a look at a couple examples. Here's 3, right? I want to take the logarithm of 5.1 and 3.0 to the negative fifth. And you'll notice I've written a negative log in front of all of these just because that's what pH does. Now, we'll need a calculator, so let me figure out that really fast. All right, so the first thing we need to do is learn how to actually enter these things into our calculator. So it's like to take the negative logarithm of 5, and we'll use the negative button. Now, it's important we use the right negative button. This minus button, the operator, is different than the negative button. So we're always going to use the negative here. Negative, and then log of 5. Okay. Enter. Again, watching again, the negative button next to the period, the log button, not the natural log, of the number we're entering, okay? So my first one here, let's see. I have 0.698. So for sig figs here, we're going to use the number of sig figs inside the parentheses. We only have one sig fig, which means we're going to get negative 0.7. Now, logarithms are dimensionless. They don't have units. So that's our final answer. All right, I want you to do this next problem by yourself, and then I'll ask it as an Edpuzzle question here. So what is the logarithm of 0.1? So notice here that the answer is 1.0 because there's 2 sig figs that come into it, and that we get a positive number now. So any number bigger than 1 inside our parentheses is going to give us a negative number when we put the negative log in. And a number smaller than 1 is going to give us a positive number when we put in a number here. And it's because this negative sign flips things around. So that's why we use the negative sign here, because most molarities in chemistry are less than 1. So we're going to be using this to keep our pH scale, between that 0 to 14 range that we'd like to. Now, sometimes I could ask you a slightly harder question like this last one, but at this point, you know what's up. I'm going to hit negative log 3.0, and then I'm going to use that second E negative 5 function, right? Just like we kind of make sense, and it's a calculator function. And here we go. I get number 4.5 something. Doesn't really matter. I only got 2 sig figs, so I'm going to take my answer here, and I want to round to the right number of sig figs, and I would get 4.5. So when you're using this, again, it's just as simple as hitting the minus button, the log button, and the number you're putting in. I might interject in a couple other spots in the video here just to show you what that calculator function would best look like. I'm going to hand it back over to Mr. Doyle now, though.
So a very simple problem might say, what is the pH of a 3.00 liter solution that contains 2.00 moles of HCl? So the first thing you want to identify here is HCl, that is an acid, right? It is a strong acid. And for our purposes, in order for you to be able to do any of the problems that we are going to do, these need to be strong substances. It needs to be a strong acid or a strong base. You can calculate this with a weak acid or a weak base, but that is something that the AP chemistry class might do. Okay, there's a lot more math involved in trying to calculate the pH of weak substances. It's a bit more complicated. But we just want to do strong substances. HCl is a strong acid, so that checks out. This is going to make it a very doable problem for us. And that's why we spent the time, again, talking about strong acids. Okay? So pH of a 3.00 liter solution, 2.00 moles of HCl. Well, our equation is the pH is equal to the negative logarithm, negative log of the hydrogen ion concentration or hydronium concentration, which means that before you do anything else, you need to calculate the hydrogen ion concentration, right? Okay, remember molarity is moles over liters, yeah? Well, here they gave us moles, so that's kind of convenient. That just goes on the top. Liters goes on the bottom, right? Volume, 3.00 liters, okay? Which means the molarity of the hydrogen ion here is 0.667 molar to 3 significant figures, okay? That is what we are going to plug into our equation to where the hydrogen ion concentration is, okay? So pH is negative log of 0.667 molar. And when you type this into your calculator, it will point back to you 0.180. Now remember a moment ago we said that pH is close to 0 means the solution is very acidic. So this would be a very acidic solution. Okay, there's a lot of hydrogen ions dissolved in that volume, 0.180. So two things to note, the solution is very acidic. And then secondly, there are no units with pH and pOH. It's just 0.180. That's it. Okay, there's no molarity or anything after, just 0.180 is the pH. Okay, and Mr. Ninnick is going to show you now, if you don't already know, what a log function is and how to type it in on your calculator.
To do that problem Mr. Doyle did. A common mistake might be to hit this minus button here, and if you do this, you'll see it says answer minus. No good. If you see that, something's wrong. You need to use the correct negative sign, logarithm, and we had the number 0.667, so we'll go ahead and enter that in. And you can see we get this answer. We'll round to sig fig, which is how we got that 0.18, and we're pretty much there. Again, the key thing is using this logarithm button here, the 1 next to 7 that says log. That's really the only new thing. All right, back over to Mr. Doyle.
So now let's look at a problem that involves one more step. And this is realistically more likely to be a real world scenario. Once again, you're not just given things in moles. Typically, you have to weigh stuff in grams, right? We don't have scales that measure moles, so we have to measure things in grams. So realistically, you're not likely to end up with something about moles of a particular acid. It's usually going to come back to you in grams. So this problem says, what is the pH of a 1.25 liter solution that contains 2.35 grams of HCl? Once again, let's make sure HCl is on our list of strong acids, so this is going to work. But I need to get the concentration of the hydrogen ion here, right? That's what I need. And since this comes apart 100%, whatever the HCl concentration is also going to be my hydrogen ion concentration. So I need to figure out what the hydrogen ion concentration is. Okay, well typically that's moles over liters. Well, we have liters, but we don't have moles. So we have to use our moles equation here, which is going to be grams divided by molar mass. Okay, so that means you need the molar mass of HCl. Hydrogen's 1.01, chlorine's 35.45, so together, adding those up, 36.46 grams per mole. Okay, the number of moles here is going to be 2.35 grams divided by 36.46 grams per mole. Okay, and typing that onto the calculator, that is to 3 significant figures, 0.0645 moles of HCl. Okay, and since this comes apart 100%, that's an important bit of information. That's why we talked about it. Okay, it's the moles of HCl. It's also the moles of the hydrogen ion, right? Since it comes apart completely. So that means I now have this value up here. I can calculate that. So my hydrogen ion concentration is 0.0645 moles, and my liters is 1.25 liters. So to 3 significant figures, 0.0645 divided by 1.25, 0.0516 molar. That seems pretty dilute, right? Okay, right, 5/100ths there. Let's plug that into the equation for pH. pH is negative log of the hydrogen ion concentration. Negative log of the hydrogen ion concentration here is 0.0516. Okay, so if we take that, put that onto a calculator, get, and the way this works actually, and we're not going to worry about it too much, is the number of significant figures here is actually indicated after the decimal. So really this is 1.287. Now we're not going to be super picky on significant figures on pH calculations, but kind of at minimum you should have 2 here. Okay, this has 3, so we should have 3 things after the decimal, 3 numbers after the decimal. That's how it works with logarithms and significant figures. So the pH of this solution is 1.287, 1.3 approximately, right? So even though this is a tiny molarity, 0.0516, it's still fairly strong in terms of acidic characteristics. Okay, let's try one with base. This says what is the POH and pH. So we're going to take advantage of that one equation that we saw, okay, back on that slide a little bit ago. pH and POH of a 10.0 liter solution that contains 40 grams of NaOH. So this is a strong base, right? It's got hydroxide in it. So when we are calculating things here, we are going to be calculating the hydroxide ion concentration. All right. So we know we need the moles of hydroxide and the volume in liters. We're going to have to calculate moles using grams and molar mass again. The grams here are 40.00 grams, and, well, if you've done sodium hydroxide enough in your life like I have, you know that sodium hydroxide is conveniently 40.00 grams per mole. Almost like I set that up on purpose. That is 1.000 moles of NaOH, right? And we can also think of that as moles of the hydroxide ion because, once again, this comes apart 100%. Okay, so we break that apart into hydroxide ions. So that's how many hydroxide ions we have in moles. Let's put that back over here. Okay, the hydroxide ion concentration is 1.000. Okay, moles divided by 10.0 liters. Okay, to 3 significant figures, that is 0.100 molar. All right, let's plug that into the POH equation because we cannot plug that into the pH equation because there is no hydroxide ion concentration in the pH equation, right? We can't start here. We can't go to this one. Okay, hopefully I'm making this clear to you. Because of this, right? The hydrogen concentration. That's not where we calculated. We calculated the hydroxide concentration. So we can't start with that one. We got to start with this one. Okay? So if you type into your calculator negative log of 0.1, okay, you're going to get 1. And technically with the significant figures here, okay, it would look like 1.000 based on how logarithms work with significant figures. So we have a pH of 1.000. How do you then find pH? Well, remember, pH plus POH equals 14. Okay, so you can find the pH by taking 14 minus POH. So in this case, 14 minus 1.000. Okay, and that 14, by the way, is an exact number. So this is 13.000 is the pH. So pretty darn basic, right? A very high pH, meaning that it's close to 14, and a very low POH, meaning it's close to 0, makes this very basic. Okay, so we're going to let you try this last one here, and then we'll solve it and see how you did. Okay, so we'll go ahead and walk you through this. You are going to need the molar mass of hydrogen iodide, which is going to be hydroiodic acid. This is a strong acid, so we know we can solve this problem. The molar mass is 127.91 grams per mole. First thing you do is figure out how many moles of acid you have. So that's grams divided by molar mass, 0.7818 moles of HI, which is also the same as the moles of the hydrogen ion since this comes apart 100%, right? So that's going to be the same thing. Finding the hydrogen ion concentration, that's moles per liter. 0.7818 moles divided by 3.25 liters from the problem is equal to 0.241 molar to 3 significant figures. And then finally, calculating pH is negative log of this value. So negative log of the hydrogen concentration, negative log of 0.241 is 0.619 is the answer there. So still very acidic. So hopefully you did well with that. If you have questions, bring them to class.